Welcome, my name is Eva Tibbetts and this is going to be a video where I do a step-by-step summary of calculus while focusing on some topics to demonstrate my understanding. To start off, calculus was first developed in the 17th century by Isaac Newton and Gottfried Leibniz and has helped the math world further understand the math that exists within our world. Calculus is basically used as a frame to understand change and prediction. Obviously, we started off the unit with reviewing pre-calculus. This was background knowledge useful to understand calculus, involving trigonometry, functions, logarithms, and graphing. But in calculus, we use all of those ideas and we dive even further by focusing on some main topics such as continuity, derivatives, integrals, and limits. Within calculus, all math is portrayed to be understandable due to having definitions, informative theorems, and problems that are provable, meaning that if a problem works with the definition and theorems discussed and given, then it has to work or it should work. The main topics I will be discussing within the calculus world will be derivatives, antiderivatives, integrals, and limits, while also connecting to other ideas as well. Derivatives find the instantaneous rate of change of a function with respect to one of its variables. This is equivalent to finding the slope of a tangent line to the function at a point. Derivatives can be used to understand functions. They can be used to describe how much a function is changing, whether if it's increasing or decreasing. One way that derivatives are often used are in L'Hopital's rule of evaluating limits. Here's an example. I'll be showing a problem that involves derivatives and L'Hopital's rule. And L'Hopital's rule is very straightforward. So let me explain. It tells us that if we have a limit as x approaches c of f of x is equal to 0, and the limit as x approaches c of g of x equals to 0, and the limit as x approaches c of f prime f over g prime x exists and equals to L, then the limit as x approaches c of f of x over g of x is going to be equal to L as well. So you can make the same statement with this just by using positive or negative infinity instead of 0. So you can just say x approaches c of g of x equals to positive or negative infinity, and you will still get the same statement as f of x over g of x equals to L. So it's very, very straightforward. So let's just say that we need to evaluate the limit as x approaches 0 of 2 sine x minus sine 2x over x minus sine x. If we just put in zeros, this will come out to be 0 over 0. So perfect, we can apply L'Hopital's rule. So assuming that this exists, we see the limit as x approaches 0 of the derivative of the numerator, which is 2 cosine x minus 2 cosine 2x. Then, finding the derivative of our denominator, it will be 1 minus cosine x. So let's now try to evaluate this limit. If we place 0 in the numerator and denominator, we will get 2 minus 2 over 1 minus 1. And we will see that 0 over 0. So this means that the limit may still exist and that we can use L'Hopital's rule again. So the limit as x approaches 0 with the derivatives of numerator and denominator is going to be negative 2 sine x plus 4 sine 2x over 0 plus sine x. So really, the denominator is going to be sine x. And once we evaluate these limits and place in 0 for our x's, we will find that it's 0 over 0 again. And we have to try again because there's a possible chance that we can get an answer. So let's take the derivative again. So the limit as x approaches 0, we will have negative 2 cosine x plus 8 cosine 2x over cosine x. And now we can evaluate and place 0, and we get negative 2 plus 8 over 1, meaning that this equals 6. It's a hefty problem and may take a little bit, but we have found an answer. And so the first limit that was asked about in the beginning, which was 2 sine x minus sine 2x over x minus sine x, will equal 6 as well due to L'Hopital's rule. Now after a hefty problem like that, let's move on to antiderivatives. These are basically the inverse of a derivative. To find an antiderivative, we typically use derivative rules in reverse, so antiderivatives are quite literally the opposite of derivatives. We can oftentimes find indefinite integrals with antiderivatives as every continuous function has an antiderivative. Here's an example. I'll be showing a problem that involves antiderivatives. Let's say we have f of x equals 3x squared plus 26 minus 9. In this, we basically will be finding derivative, but instead of reducing the exponent, we'll be adding to it and then divide, which you'll see in a second. So you see we have 3x squared. It will turn into 3x cubed over 3, meaning just 3 cubed. Whatever the exponent becomes, that's what you divide. We do this to the entire problem. So 26x will be 26x squared divided by 2. And then we have 9. But 9 doesn't have an x. So instead of doing the whole exponent thing, we add an x to the 9. So overall, it'll be capital F of x equals x cubed plus 13x squared minus 9x. But don't forget c. There'll always be a constant. This is because when you take derivative, we typically get a number. So that c acts as a place for that number because we don't know if there's a number or not. So you'll officially have capital F of x equals x cubed plus 13x squared minus 9x plus c. As mentioned before, integrals are also opposites of derivatives. Integrals are seen to represent an area, often describe the area under the curve due to representing that area. They can be separated from definite and indefinite, which clearly represents whether or not the area is in a specific space or continuous. I'll be showing a problem involving indefinite and definite integrals, but to spot the difference is that one has bounds and the other does not. Think indefinite is infinity, so no bounds. So let's say we have an indefinite integral of 4 dx. It will simply turn out to be 4x plus c. We got this by using antiderivative. As you see, we're adding x to 4 and also c to the end. We are reversing the steps of derivatives, as we did before. So let's do another problem that involves indefinite integrals. We have to find the antiderivative of this integral of 3x minus 1 squared dx. To do so, we will FOIL. We'll have 3x minus 1 dx. And this will create 9x squared minus 3x plus 1. We're going to have to combine like terms and lead us to have 9x squared minus 6 plus 1 dx. So now, we will find the antiderivative as we did before, so we can easily just do this in our heads. So now we'll have 3x cubed minus 3x squared plus x plus c, and that is our final answer. Now I will show you a definite integral problem. So let's evaluate 8 dx from 2 to 5. First, we need to find the antiderivative of 8, which is 8x. And now we will evaluate it. We will replace x with 5 and also replace x with 6. But we are subtracting between these bounds, so it will be 8 times 5 minus 8 times 2. So 40 minus 16 will be 24, which makes sense because with definite integrals, we should be getting a number. It's truly as simple as that. Now moving on to limits. Limits show the value of a function as its input is approaching a number. Limits are used throughout calculus, being one of the backbone necessities within this subject. They are used in integrals, continuity, and derivatives. I'll be showing a problem involving limits. So let's say I have f of x equals x squared when x cannot equal 2 and 1 when x equals 2. We'll draw a graph and place our numbers, and this will look like a parabola. On our graph, you will see an open circle at x equals 2 and y equals 4. This is because there's some discontinuity due to x squared not being able to be at 2. And then elsewhere on the graph, at x equals 2 and y equals 1, there's going to be a filled in dot due to x being able to equal 2. Though it's not on our parabola, it's important to have on our graph. Now from here, we can see a limit as x approaches 2. Well, what is gx? We aren't concerned about x-axis, but instead the parabola. So looking at where the open circle at x equals 2, we are going to be viewing how we approach it on either side. And 4 is where g of x should be approaching. So this means that limit as x approaches 2, g of x equals 4. Now, my presentation is over, and I would like to thank you for watching my video, and hopefully you and I were able to connect on some great ideas that are within the unit of calculus.